I will undo to redo the EQ. Okay. Whatever you do to the EQ, I will undo to redo the EQ. Good enough. Equilibrium. I have here 2 vials of NO2 and of this stuff. Really cool. This is one of my crowning achievements. This was not easy to make. Hopefully someone will never open it up. I'm going to put 1 vial in the hot water. I'm going to put 1 vial in the cold water. They're exactly the same thing, and I don't know which one is which. They're exactly the same thing. I poured the gas into both of them and then sealed it up. And this is the equilibrium. NO2 is in equilibrium with N2O4, and it needs some heat. So what I've done here is I put 1 of them in cold water and 1 of them in hot water. 1 of them is NO2, and 1 of them is N2O4, the 2 molecules in there. And there's a mixture of both of them. When I put the vial in the hot water here, I created a stress. And the stress was too much heat. So the equilibrium shifted to undo that stress. What direction do you think the equilibrium shifted? It shifted to the left. Equilibrium shifted to the left.
Yeah, that's what I'm saying.
So whatever you do to the EQ, I will undo to redo the EQ. I increase the heat, that shifted the equilibrium to the left. In other words, the stress was too much heat, and to undo that stress, I reduce the heat by shifting the equilibrium to the left. Also, the one in the cold, the one in the cold, I reduced. Do I need to turn the light on so you can see the vials a little bit better? Okay. The one in the cold, I reduced the heat because I put it in cold water, and now the stress was not enough heat. What direction will the equilibrium shift?
Right.
To the right. Okay. So if I heat it up, the stress is too much heat, equilibrium shifts to the left. If I cool it down, equilibrium is not enough heat, and the equilibrium shifts to the right. Make sense? Okay. So my question for you is, which one of these 2 is the dark compound? One of them is dark and one of them is colorless. This is the hot. This is the cold. Which one, NO2 or N2O4, is the dark? Take about a minute and chat with your neighbor.
He literally just microwaved the water up.
So one of them is a dark brown and one of them is colorless.
Maybe. I don't know. When you make something colder, it has a lighter color.
All right. If you believe that NO2 is the dark one, raise your hand. Okay, wait, you're like, I'm not sure what you're asking, Mr. Price. Okay, so one of these 2 is dark brown, and one of them is colorless. So if you had a container of just one of them, it would be dark. If you had a container of just the other one, it would be colorless. So who thinks the NO2 is the dark one? And you're right. It is the dark one. And this one's colorless.
That's what my brain said.
So when you heated it up, the stress was too much heat. So you shifted the equilibrium towards the NO2 side. This one has more NO2 because it's hot. This one has more N2O4 because it's cold. Hot, cold. You can switch them too, and they'll go back to each other. Water's not hot enough. Do I need to switch them, or does that confuse you?
Switch them.
Okay. I want to see what will happen. All right, cool. Next, we're almost done.
Wait, I don't know.
Here's the abbreviated book definition. A system at equilibrium will change to resist stress at equilibrium. Up and over, down and 2. So anytime you have a stress that causes one side to increase, that's going to cause the equilibrium to shift over the equilibrium side. So more on one side would shift the equilibrium over the equilibrium. Up and over. If you take one away, that will shift the equilibrium to whatever was taken away. So up and over, down and 2. The stress was too much heat. Equilibrium said, okay, there's too much heat in here. I'm going to have to change the equilibrium to take the heat away. And to take the heat away, it made more NO2. When in the cold water, there's like, whoa, there's not enough heat. I better make some more heat. So the heat was too little, equilibrium shifted to make more heat. Up and over, down and 2. Okay, how are we doing so far? Give me a thumbs up and great to move on. Looks like most of you, so off we go. All right, vapor pressure. We talked about vapor pressure last time, and we talked about how all things have a vapor pressure, all liquids have a vapor pressure. So we talked about this, all liquids have vapor pressure. Some are better at making vapors than others, and those things that are better are called volatile liquids. Volatile liquids tend to have a lot of energy. They have a very high kinetic energy, a smaller intermolecular force, so they tend to boil really easily and exert high vapor pressure. Hey, look, it switched. Now this one's darker.
They were the same color.
Yeah, they're the same color for a little while.
You can have whatever color you want to be.
As long as it's black. The Model T is available in any color. As long as it's black.
Yeah.
Okay, guys, we have one more thing to talk about. So, scribble what you want to scribble about volatile liquids. Then we're going to talk about something really cool called phase diagrams.
What would light be considered?
Oh, what?
Light.
Light? Light are energetic photons of electromagnetic radiation that your eyes detect and color. Say, that's a blue light.
So,
Not a phase. No. It's energy. It's a photon of electromagnetic energy or electromagnetic wave. Okay, let's move on. Phase diagrams. Phase diagrams are really neat. We have an activity either Monday or Tuesday on phase diagrams, and phase diagrams are they show what phase of matter will exist at certain pressure and temperature conditions. Okay. So this is a phase diagram. Pressure is on the y-axis, and this is 1 atmosphere right here. Right now it's 101 kilopascals, but that's 1 atmosphere right there. And down here, this is 100 degrees Celsius, and this is 0 degrees Celsius. You can't see it. So if you said, okay, this compound, whatever this substance is, at 1 atmosphere and 75 degrees Celsius, what phase is it? You're like, okay, 1 atmosphere, 75 degrees. Oh, it's a liquid.
I like this.
What if you took that 1 atmosphere and you cranked the temperature up to 150 degrees Celsius? Oh, it's a gas. And what happens at 100 degrees Celsius? The liquid and the vapor are in equilibrium with each other. These are equilibrium lines. Any pressure-temperature combination that puts you on the line puts you in equilibrium. Taylor.
What state is it in at triple point?
At the triple point? All 3. Yeah. Since you talked about the triple point exists at that very specific combination of pressure and temperature. All 3 states exist. Yes?
Can you show us a video where that's occurring?
That's a great idea. Brandon, did you have a question was that your question?
No.
Okay. So yes, we'll show a video. But I have something else first. So let me bring up the notesy part, and then I want to remind you of something. Okay, so the boiling line, every point, every pressure temperature combination on this line is an equilibrium between a liquid and a vapor. It's boiling. And everywhere in this line right here, there's an equilibrium, actually right here, there's an equilibrium between a solid and a liquid. It's freezing and melting. And then of course, I didn't even put it there, it's sublimation. This tiny little line right here, that's the equilibrium between solid and gas. Water can sublimate? Sure it can, everything can sublimate, for the most part.
Gas sublimate?
A gas cannot sublimate, a gas can deposit, but it can't
Where's the
sublimate.
plasma, bro?
It's over here. It's where,
Past kryptonite.
it's where the temperature is so high that the electrons have flown off.
What about the black matter?
The Bose-Einstein condensate, that's way down there. All right, so I did this before, but if you didn't see it before, or you want to see it again, I'm going to show it to you again. Oh, by the way, this phase diagram is for what compound?
Fluid.
Water. It's for water. Okay, because at 1 atmospheric pressure, water, it freezes and melts at 0 degrees, and it boils and condenses at 100 degrees, so it's water. Okay, so if you remember this, this water is, when I keep my finger in it, probably about 65 degrees, maybe 70 Celsius at best. So we're at atmospheric pressure, and the temperature is about 65, maybe right about there. Okay, so right now, this compound here is what phase? Liquid. I'm going to suck some up. Still, what is it?
Liquid.
It's a liquid. Then what am I going to do? Take the pressure away. Now what is it? It's boiling. Yay! Yeah. Okay. So again, liquid, but when I take the pressure away, it's actually really not. It's like room temperature plus maybe 20.
Rome said it was toasty.
It usually is, but this water is cooled down quite a bit. So it's maybe 50 or 60 at
So
most.
will that not work with cold water?
It won't, because I can't make it cold. I can't drop the pressure enough. So what I'm doing is when I'm dropping the pressure, I'm driving the pressure down here to where it can boil. I can try it with cold water. Cold water, this is like almost freezing because it came out of ice water. So the freezing temperature, it's basically probably right about there. If I drive it down the same pressure, it's still going to stay a liquid.
Yeah.
So I can try it, but I don't have a lot of confidence it's going to work. Right, if I drive down the pressure, yeah. Okay, so this is the cold one.
Up a smaller amount.
Yeah, like
than
a lot
twice.
smaller.
Well, it's still boiling a little bit. Huh. Apparently I made the pressure, the bubbles were very small, but it bubbled a little bit. Certainly not as well as this one did.
Yeah. That's cool.
Yeah. So apparently I'm driving the pressure down here somewhere. But that's how it works.
Because you're just so small.
Because you could drive
I am
it
swole.
with a triple
Okay.
shot.
Questions? All right, we have a video. I'm going to start the video and then we kill the play. Okay. 7 minutes, which should be just about right.
Testified that the CIA withheld intelligence from the FBI. They've been lied to.
Boiling.